Huh? Yeah, we'll talk about grounding again. We had a long discussion yesterday morning at breakfast on grounding.
Oh, well, the top three next debate and conversations. Yeah, I follow a couple of pages on Facebook. Most of what comes out on there is just useless to me, but I do find things on there and I can ask questions on there. But yeah, anytime the grounding, somebody their first day, inevitably, their first day on the group, they want to say, I'm having problems figuring out how to ground my station.
And you get 15 different answers.
They've got 500 responses.
Yeah.
But I don't think,
Okay. Uh, wait another minute for Nelson to get back, but uh, the first line is very important. There's a lot of things in amateur radio that you may not suspect that can be deadly. Antennas, for instance, uh, if not deadly, create some serious RF burns. If you got power amplifiers, you're talking as particularly tube type. You're talking some very high voltages and currents that are possible, well above the 30 volts and 100 milliamps, which uh, anything above that can actually cause death. Uh, and it's basically due to current flowing through the body. So you can get involuntary muscle contractions if the current is low. And as the current gets higher, you can actually get burns because it'll heat the tissue up. You're looking like a resistor. Um, and you can actually get enough, particularly when the voltage gets up, to disrupt your heart uh, signal. So your heart goes into fibrillation, and they get you out of fibrillation by giving you another shock. I can attest to the involuntary muscle contraction, having been shocked a few times by 120 and higher. And it's kind of like getting hit by a 2x4, and you definitely have your muscles contract. What health hazard is presented by electrical current flowing through the body?
All of them.
Delta.
the rest of it, I can stop at reading.
In the United States, we have, for the code nowadays, 3-wire outlets, even though there's still places that have 2. Um, and with a 3-wire outlet, you have a third ground pin called a safety ground. And that's the reason it's there, as a safety for an electrical short in a piece of equipment like an appliance, a power drill, something like that. If it shorts internally, particularly if it's something with a metal case, uh, that is connected to the safety ground, which goes back to a ground rod at your service entrance where power comes into the house. And that's supposed to divert the current to ground as opposed to through you to ground. You might still feel a tingle depending on how far away you are from your uh, service entrance. You need to have all of the equipment in your station, and most everything you buy nowadays, be it a watt meter, radio, most of the accessories will have a ground lug on it. So you can connect these all to a common single point, what we call a single point ground. In some cases, people will use a piece of copper pipe mounted and connect everything to that pipe and then connect that to a ground rod outside. In some cases, maybe a big flat copper bar or uh, an entrance panel in the window that's metal that's connected to ground. There are different ways to do it, but the idea is to try to make it as close to a single point connection for everything, so everything is at the same potential. So if the ground potential rises, everything rises with it, so there's no difference in potential, which is what's required for current to flow. So if there's no potential difference, there's no current flowing. You normally use either a copper strap, a braid, or heavy gauge wire to connect your grounds indoors. It's not recommended to use braid outside because it oxidizes and disintegrates. So you should either use copper strap or a very heavy gauge, at least 6 gauge or larger ground wire. And if you have anything like, tube amplifiers, things like that, that has any kind of high voltage, you need to make sure that it's got some kind of interlock where if you take the cover off, it disconnects it from the AC power. It still doesn't prevent you from having high voltage capacitors that still have a charge on them. But at least you're not getting AC power in there. This is a chart showing a typical where your power lines come in. And coming into your service entrance, and there you'll have the power company will have put a ground rod in, and it'll be connected. And it's usually not a very big wire. It's definitely not a number 6, because they're looking at being a safety ground, so you're not talking about much current. It's certainly not for lightning protection. And that safety ground is connected all through your house. So everything plugged in to your AC power is connected to that same safety ground. So if you were to have an lightning strike out here on the power line, or induced close enough to it where it's going to induce a current, that can come through the house wiring. And even if you've got a shack ground over here, these are only connected with this number. Oh, yeah, it's usually not 12. 14, 16, something like that. So it's fairly high resistance and inductance for a lightning strike. So you should have a heavy gauge connection between your shack ground and the service entrance, which is why I call this a bad grounding thing without those being connected and bonded together. So in the United States, did I miss that chart? Okay.
No,
No, it was there.
Okay, I just didn't read it or say it.
kind of confusing, because it's not the same as an electronics technician.
Right.
Black lanes.
Yes. We normally use black for ground.
Yeah.
Or for zero potential, neutral, wherein AC or power distribution, the black or the red insulation indicates the hot lead, and the white or off-white, called neutral, is the neutral. And then usually green to represent the safety ground. If you have 240 volt, you have two hot lines. So one will be black and one will be red. And they distinguish them because they're 180 degrees out of phase. So you can't connect them together. It makes a big spark. So black is the hot. What is a good way to guard against electrical shock at your station?
Delta.
Delta.
All of the above. Okay, fuses and circuit breakers. Their purpose is to remove power to try to prevent excessive current. And the circuit breakers and fuses both set to, in essence, trip or open at a specific current. Now, neither of them operate very fast. Fuse is probably faster than a circuit breaker. So you can still have some currents that exceed the rating on your circuit breaker or fuse for a short period of time. But at least they will stop it from continued excessive current where you could actually get enough heating or overload to cause a fire. So that's really the purpose. You never want to put in a fuse or a circuit breaker that has a much higher current rating than the load that you're supplying. So in the case of a piece of equipment, and let's say it's got a fuse in it in the back, and it says it's rated for 5 amps, you probably don't want to put more than a 5, maybe a 6 amp fuse in there, certainly not a 10 or 20 amp fuse.
Something else inside will burn up first, but not the fuse. So
And then you get a fire and, you know, smoke detector goes off and the fire department comes.
Should wrap little fuses in the car with aluminum.
No, and you shouldn't do what we did back in the old days when you went down in the basement and you actually had screw-in fuses and you didn't have the right one, you put a penny in.
Yeah, you didn't know. Or the ones in the car, just wrap it in aluminum foil when I didn't have any. Put it right back.
But you got a proper one right away, right?
Yeah. Relatively right away.
putting it in for repair all the time, that you open it up and you look at it and you say, you're lost. You don't know where to start because everything's burned up. And then you start investigating and you find somebody has soldered a piece of bus wire across the fuse.
So what's the purpose of a fuse in an electrical circuit?
All of the above.
Are we sure about that? Let's see. Did we talk about power supply ripple?
Nope.
Mentioning a component.
But that's a design problem.
Fuse doesn't really limit current. Like allow this much current to flow.
Yeah.
But no more.
It allows current up to where it opens.
Slows and removes the current.
And it won't prevent shocks by limiting the current. It will supply as much current as it's rated for before it opens up. So consider that a trick question. Where should a fuse or circuit breaker be installed in a 120 volt AC power circuit? I don't think I talked about that either.
It's there somewhere.
Yeah.
In series though, with the hot one.
Right. In the hot conductor only, not on the neutral.
Change with the mobile.
And in series, not in parallel. These two parallel are definitely throwaways.
Yeah,
Because you do it in parallel.
It's
it's kind of pointless.
nothing.
It's like, oh, look, there it goes.
Why should a 5 amp fuse never be replaced with a 20 amp fuse?
Charlie. Charlie.
Just showing.
Yeah, I would go with Charlie, but then I know the answer.
I guess in my head, I had the question backwards.
I've taken this exam a few times. Always disconnect power before working on equipment. If you've got any kind of power supply at above 30 volts, they can store a charge and at least give you a serious shock, if not enough to cause fibrillation. So you need to make sure that any of those higher voltage large capacitors are discharged. In a normal design, there will be a what we call a bleeder resistor, which is a fairly high value resistor that when the system not powered up will discharge the capacitor over time automatically just by draining the charge out of it. So you can measure the voltage on the capacitor to see if it does have a charge on it. I've seen some things on building a little shorting wand that you connect to ground, and you can actually connect it to touch it on the terminal and it shorts it to ground to discharge it. It's obviously something insulated from your hand. And the other rule, which is very important, is when you're working on that kind of stuff, try to keep one hand behind your back, because current flowing from hand to hand goes through your heart, and that can cause fibrillation. If you're only touching it with, say, your finger, then it has to go from there to ground, and it's not going to have as big an effect on your heart as if you're doing it straight through arm to arm. Sometimes you can't work with one hand, but it's really a good idea to do that. What hazard exists in a power supply immediately after turning it off?
The charge in the capacitors.
Sounds like Delta. Okay, storage batteries. We're talking like typical lead acid battery, like you find in your car, or smaller ones that you see in some of these uninterruptible power sources, or emergency lights use the same kind of battery. They're capable of extremely high current. If you notice on your car, it'll list the cranking amps, and it's in hundreds of amps. So they can deliver a tremendous amount of current, even though it's only 12 volts, 13 actually. So shorting the terminals with something like a screwdriver or wrench or something conductive will turn that conductor, screwdriver, wrench into a filament and turn it at least orange to yellow, extremely hot, enough to cause a fire. Also, that rapid discharging in that case would cause possibly outgassing of a lot of hydrogen from the sulfuric acid in the battery. So now you've got hydrogen and oxygen and a heat source. which can go poof. You ever seen a high school thing where they take a tube, and generate hydrogen and oxygen and hold a match and it makes a nice little explosion? And also, if you got enough heating and outgassing, which is creating pressure in the battery, you could actually have the battery case explode. So now you've got it spewing sulfuric acid around. And that's not good stuff to get on you. Which of the following is a safety hazard of a 12-volt storage battery?
B.
Come on,
Going
Nelson.
between A and B,
Delta.
and I'm thinking maybe Delta. I don't know about C though. So I'm lost.
Okay. Well, I can tell you C's not the answer.
All right. So then, Bravo.
Okay. And what did we say in the beginning about, before we talked about batteries, about what voltage and current was a problem? 30 volts, right? And the batteries, how many volts? So most people can put their fingers across a 12-volt battery and not really feel anything. There's probably some exceptions, but it's not gonna
It's
not gonna hurt you.
torture mechanism on movies all the time.
Yeah, I don't know about that.
So the phenomenon that you get when you touch a 9-volt battery to your tongue is because of the moisture. Okay, so I used to teach this all the time when I was teaching basic electricity and electronics in the Navy. Was that, when you're on a ship at sea and you're working, you've got a job to do, and you gotta get it done as quickly as possible. So you're probably perspiring a little bit. So your normal 100K or 200K body resistance drops because of the moisture in your skin is, that reduces your resistance. As the resistance goes down, voltage stays the same, current still goes up. So the current that goes through you, and a guy demonstrated it one time for us. He grabbed a 2100 volt power supply, and in one hand, while he had his other hand on the case of the electronics that he was troubleshooting. And he was in a hurry because he wanted to go home early that day. He left the shop early, but he didn't go home for 2 days because he went and sat in the hospital over the weekend.
Yeah.
She survived.
Yeah, he did. He survived it.
That very first line on the first chart was important. It can be deadly.
Mhm.
So touching terminals of a 12-volt battery in most cases isn't going to create a shock per se. You might feel the current. In RF emissions, I guess technically if you had many kilowatts, who knows?
Transmitter, what?
Yeah, I think RF emissions normally have no effect on a battery. What hazard is caused by charging or discharging a battery too quickly?
Alpha.
I'll go with alpha.
I don't know how to zero, but
Yeah, most batteries have a stated maximum charge and discharge value, and it's usually in C, where C is the amp hour capacity of the battery. So a lot of the lithium batteries are used for radio control airplanes. They're now up to 20, 40 C or higher discharge rate. So with say a 1 amp hour battery, it means it could discharge 40 amps. Now you normally charge them at like 1/10 of a C. Okay, so we learned that shock can cause damage due to heating of a tissue, which is a burn. It could disrupt cell functions like your uh, heart muscle and interfere with the signal going to it. You can definitely get muscle contractions. I can verify that. You should use 3-wire cords and plugs and not really one of these little cheap adapters. Try to connect everything through a low resistance wire to a safety ground, which is why copper strap or copper braid, because there's a large surface area and current actually travels on the surface of conductors. And have mechanical interlocks in high voltage equipment to at least turn the power off if you open it up. Fuses, they're there to remove the power in case of a current overload. You install them in the hot lead. Never put a larger fuse than rated in the circuit. If it's a power supply, you could have high voltage on the filter capacitors, even when it's turned off. And it's possible that they don't have a bleeder resistor at all. So a good quality capacitor could hold charge for quite a while. Would depend on its internal resistance and leakage. Storage batteries, shorting them can cause extremely high currents, which can cause burns, fires, explosions due to the outgassing and overheating, overpressure it. It's pretty much a sealed unit, so when you really heat it up, you get a lot of pressure inside.